Good morning, everyone. Today we're going to talk about double replacement reactions. So you watched a short video last night that went through some of the basics, and we're really going to focus today on A, predicting what the products of a double replacement reaction would be, and B, predicting whether that reaction is going to happen or not. Because just like single replacements, sometimes it will happen, sometimes it won't. So you'll have the tools that you need to figure out whether that will happen by the end of today. I uploaded some notes for you on Schoology that I'm going to go through. They are the PDF slides of a PowerPoint. I figured by uploading them, you can focus on what I'm saying and jotting extra things down that you need to, as opposed to spending the time to write everything down. So if you haven't already, pause this, go to Schoology, download those so you can follow along and you can add on to them as you see fit. I'm going to pull up the notes here and we will start to go through some of them. All right, so as a reminder, double replacement reactions. In a double replacement reaction, there are two ionic compounds and they swap partners. So you've got two ionic compounds and you're going to end up with two ionic compounds at the end as well, but they're going to be different pairs of cations and anions. You have an example of a double replacement reaction here where we have silver nitrate and copper 2 chloride yielding copper 2 nitrate and silver chloride. And I realized very quickly after I uploaded these that I messed up on the one subscript. So I went ahead and changed that. Copper 2 nitrate should be aqueous. And we will talk a little bit later about how you'll know what state something should be, because that's going to be the big point as far as whether the reaction is going to happen or not. The question I want to ask here is, do any of these elements change their charge from side to side? So if you remember in a single replacement reaction, we had elements on the reactant side and product side where their charge changed. They were neutral on one side and they might have had a positive charge on the other side, but they were neutral on one side and they had a negative charge on the other side. Let's look first at, in a double replacement reaction, are the charges going to change? Let's break each of these compounds apart and take a look at that. So if I look first at silver nitrate, I'm going to split each of these apart into the cation half and the anion half, and then just check them out from side to side and see whether any of these things change their charge. So silver in a compound, remember it is a transition metal, but it's one of the ones that's charge is never going to change as long as it's ionic. It's always going to have a charge of +1. And then NO3, our anion nitrate, is always going to have a charge of -1. That's one of the ones that you had to memorize way back when. If we go to our other reactant, the copper chloride, well, copper has some options there. It might have different charges in different places. So we need to use our anion to figure out what the charge of copper is in this particular compound. Chlorine has a charge of -1. I have two of them. So total negative charge in this ionic substance is -2, which means that my copper must be +2. So on my reactant side, I have silver with a charge of +1, nitrate with a charge of -1, copper with a charge of +2, and chloride with a charge of -1. Let's look and see on the product side whether those things have the same charges or not. So again, I'm going to split up my cation and my anion. Nitrate, -1. I have two of these, so total negative charge is -2, which means that my copper does still have a charge of +2. And then silver is still part of an ionic compound, so it still has a charge of +1, and chloride has a charge of -1. So if you take a look at this as a whole, and we compare both sides, you can see that all of my ions retain their charges from the reactant side to the product side. Nothing's going to change. And that's different than, again, when we talked about the single replacement reactions. What I do want you to pay attention to, though, here, because this is going to be a big thing when we're predicting the products of these reactions, notice that nothing changes its charge, but the subscripts that follow some of these ions are going to change. Now let's look specifically at the chloride when we're looking at this. On my reactant side, there are two chloride ions. And I got that too because it needed to balance out the charge of the copper, okay? On my product side, there's only one. So I want you to pay close attention to the fact that this subscript of 2 after chloride does not necessarily follow it from side to side. You need to take each individual compound and balance out the charges to figure out what the formula for that compound is going to be. The only subscripts that will follow from side to side are those that are part of the polyatomic ion. Not saying how many of the polyatomic ions you have, but those that are part of the polyatomic ion. So, for example, this 3, that's part of the nitrate ion, the NO3, does go with the oxygen because it's part of the formula for the polyatomic ion. Now, on my reactant side, I only had 1 nitrate, and on my product side, I had 2, again, because it needed to be balanced out charge-wise. But the subscript only follows if it's part of the polyatomic ion. So charges don't change from side to side. Subscripts do not follow from side to side. We need to take each individual compound and the charges of things that are within that compound into consideration when we're writing the formulas. The only subscripts that are going to go from side to side are going to be the ones that are part of polyatomic ions. Okay? We're going to take a second and we're going to watch an example of a double replacement reaction. This is from the same video I showed you guys an example of a single replacement reaction before. So she's going to go through some an analogy with some Barbie dolls and then go into the lab and show you an example of a double replacement reaction simulation. So I'll go ahead and play that for you.
In the fourth type of chemical reaction that we're going to talk about today, it's called a double replacement. In a double replacement chemical reaction, you typically have 2 compounds that are dissolved in water. When you add the 2 compounds together, you typically create 2 new compounds. One of the 2 is what we call a precipitate, or an insoluble compound, a compound that does not dissolve in water. When we look at this with our friends, the Barbies, let's see what this looks like. As we learned in a previous demonstration, Anthony and Karima become quite a couple. They decided they would go to prom together, and they were very happy on the dance floor and having a great time. However, we also knew about Liliana. Well, Liliana was not one to stay at home and be sad. She went out and found herself a new boyfriend. Liliana's new boyfriend is named Colin, and Colin and Liliana also decided that they would go to prom. So on prom night, both couples are on the dance floor and having a great time. But in the middle of a song, a very romantic song, Liliana notices that Anthony is, you know it, checking her out. And the love returns. And so in the middle of prom, here's what happens. Liliana decides that she wants Anthony back. And so they go back to being a couple. But Colin and Karima are there to have a good time. So they're not going to go off on their own and pout. They decide to become a new couple as well. We call this the prom switcheroo. Essentially, the ladies have switched dates. They started off with one man, and by the end of the prom, they're with another man. A great example of a double replacement reaction. In our next chemical reaction, I'm going to show you a demonstration of a double replacement. Here are the chemicals that I'm starting with. So my first reactant is a solid chemical that's called cobalt 2 chloride. If you zoom in and take a look at this, it's a really pretty pink color, but right now it's in the solid state. So I wanted to show you what I'm going to do with this I'm going to take the solid cobalt chloride, and I have some deionized water. And I'm going to put that in there. And the reason I wanted to show you this is I wanted you to understand that what I'm making is called an aqueous solution. So the solid cobalt chloride is dissolving in water, and we are making a homogeneous mixture, which in chemistry we call a solution. And this is going to be my first reactant. Okay. So once I get the cobalt chloride nice and dissolved, which I think it is now, really pretty color. Okay. I'm going to pour it into this nice clear plastic cup, so it's really easy for you to see. That's the only reason why I'm using that cup. The second chemical reactant is in this large jug. So this is a chemical that's already pre-made for me. It's a solution that is called sodium silicate. And so in a double replacement reaction, what you typically see is both compounds have been dissolved in water. So we're dealing with two aqueous solutions. Aqueous means water-based, so the chemicals have been dissolved in water. So I'm going to take the second reactant and add it to the first reactant, and notice what happens when the two are combined. So I love the color of this product. This is what we call cobalt blue, and it's got a really beautiful deep blue color to it. And I'm going to take a stirring rod and just stir it up a little bit, and notice the solid that has been created. So one, I like this because I think it's really beautiful, but two, I want you to visually see that a precipitate has been created. Remember what a precipitate is. A precipitate is a solid that forms in a chemical reaction. So we're making something that is not soluble in water anymore. And so what we've got as our products, there's actually two of them. One of them is called cobalt-2 silicate, and that's that really pretty blue chunky solid that you see created in there. And the other one is merely sodium chloride. Now, sodium chloride does dissolve in water, and so that is still floating around in the water that we've got here. But what's most noticeable, of course, is the chunky precipitate that we created, which is insoluble in water. And that is typically what we look for in a double replacement reaction, is when two aqueous solutions are combined, a precipitate is typically created as one of the products of the chemical reaction.
All right, so I'm going to exit out here. All right, so let's take a look at that reaction that you just saw in the video there. So both of your reactants there, the cobalt-2 chloride and the sodium silicate, both of your reactants there were in the aqueous phase when they started. And notice what you saw. You saw a color change. You saw a really noticeable chunky solid precipitate forming. You saw a bunch of signs that a chemical reaction was happening. In the video, you saw and you were told that the products of that reaction were cobalt-2 silicate and sodium chloride. So cobalt-2 silicate was that really chunky blue precipitate, and then sodium chloride was the clear looking solution that you could see at the bottom of the cup once things were mixed together. Cobalt-2 silicate, we've got cobalt with a charge of +2, and then silicate, which is not something that I would expect you to know off the top of your head. SiO3 has a charge of -2. So if these two things were to come together, the formula should just be COSiO3. So I'm going to go ahead and put that together. And that was your precipitate. We'll talk in a couple minutes about how you would know that that's the precipitate. Shrink this all down a little so it all fits here. And then your other product there was the leftovers. So I took the cobalt and the silicate here and I put them together. So the other product is going to be the sodium paired up with the chlorine. And I'm hoping that by this point in time, you realize when sodium and chlorine come together, you get sodium chloride, NaCl, salts. And salt was that clear, aqueous, however you want to say it, solution that was in the bottom of that that tube that you were looking at. Okay. To balance this, we need a 2 here. All right, so there's another example of a double replacement reaction. What we're going to go through is first predicting the products of double replacement reactions. So if you didn't see that and you weren't told that cobalt 2 silicate and sodium chloride were the products, how would you predict what those products are? And then how do you know whether the reaction happens or not? What needs to happen or what needs to be the case in order for a reaction to happen? In single replacement reactions, we had that activity series we used. In double replacement, we're going to look at something else. So in the video that you guys watched last night, you were told to first combine the inner ions, then the outer ions to predict what the products were going to be on the product, or what the substances were going to be on the product side of the reaction. So when you're predicting products, combine the inner ions first and then combine the outer ions. Always make sure you keep the positive cation written first. And remember that the ions keep their original charges from the reactant side to the product side, which means that the subscripts may change. They don't necessarily travel with the ion unless it's part of the formula for a polyatomic ion. I guess you have 2 copies of that page. I apologize. All right, let's go through and let's predict the products for this double replacement reaction. So combine the inner, combine the outer. So I'm gonna focus in here. I'm gonna split these things up into ions. So I've got positive, actually I will write what the charges are. I've got +2, -1, and then over here, sodium has a charge of +1, phosphate has a charge of -3. I'm not worried at all about this subscript. I'm not worried at all about this subscript. I am going to keep the 4 with the phosphate when I'm predicting what my products are going to be. So I'm going to combine the inner, which means that I'm going to end up on my product side with sodium, which has a charge of +1, paired up with chloride, which has a charge of -1. I wrote the positive first, I wrote the negative second. And then I'm going to combine the outer. So I'm going to end up with calcium, which has a charge of +2, paired up with phosphate, which has a charge of -3. So let's go ahead and write what these products are going to be. Well, the first one is just going to be NaCl. And the second one is going to be formed from calcium +2 and phosphate -3. It's going to be Ca3 PO4 2. All right, so I have calcium chloride and sodium phosphate yield sodium chloride and calcium phosphate. Now, if you switch the order, if you put the calcium phosphate written first and the sodium chloride second, it makes no difference. It is important to put the cation first and the anion second. Last step to this is to balance it. So on my reactant side, I have 1 calcium. On my product side, I have 3. So I need to make sure I put a coefficient of 3 in front of my calcium chloride. My other metal, on my reactant side, I have 3 sodiums. On my product side, I have 1. So for now anyway, I'm gonna put a 3 here. That might change. My next is my polyatomic ions. So on my product side, I have 2 phosphates. On my reactant side, I have 1. So I need to put a 2 here. Now that changes sodium, but let me just finish things out. Most of the time they'll work themselves out. My last thing I need to balance out here is the nonmetals, my chlorine. My reactant side, I have 3 times 2, I have 6. On my product side, I only have 3 right now. I need to change that to a 6. And that ends up fixing my sodiums as well. So I would just do a quick pass through, make sure everything's fine, and it should be all balanced out. So here is your balanced chemical equation for the double replacement reaction between calcium chloride and sodium phosphate. We combine the inner 2 elements, and then we combine the outer 2 elements. All right, but how do you predict if the double replacement reaction is actually going to occur or not? Just like with single replacement reactions, not all double replacement reactions will occur. Remember with the single replacements, how we estimated or figured out whether they were going to happen or not was by using that activity series. How we're going to figure out whether the double replacement reactions are going to happen or not is by looking at what the products are. So here's your rule. In order for a double replacement reaction to occur, at least one of the products must be insoluble. That means, I'm going to highlight that because it's important. Basically, what that means is both of your products cannot be aqueous. One of them, at least one, has to be either a solid, a liquid, or a gas. So that begs the question of how do you figure out what state things are going to be? Well, first of all, there's a couple substances that might show up on the product side that are non-ionizable. And those things would be water or maybe ammonia, NH3. You should know that both of those, if they show up, are going to be liquids. If one of your products is water or ammonia, you are pretty safe to say that that reaction occurred. If one of your products is a gas, that reaction occurred. Some common gases that you might see are carbon dioxide, sulfur dioxide, nitrogen dioxide, these more covalent substances. Not super likely gonna happen, but it's a possibility. They could maybe show up. If one of these is your product in some way, shape, or form, it's a gas, the reaction will occur. The big one is, what if I have 2 ionic substances? Sometimes those ionic substances are soluble, sometimes they are aqueous, sometimes they are insoluble, and that means that they are a solid precipitate. So there's a couple rules that you need to know to figure that out. If your cation is an alkali metal, so alkali metal would be something from group 1. Hydrogen, we're counting that in that group because it's in the group of them. Hydrogen, lithium, sodium, lithium, any of those from group 1. If your cation is something from group 1 and or your anion is nitrate, NO3, or acetate, C2H3O2, or any way that you're going to write it, CH3COO. If any of those things are true, then your substance is soluble. In other words, it gets a little AQ behind it. If you have any other combination of cation and anion, your substance is insoluble, a precipitate, a solid. So it would get an S behind it. So again, your reaction, your double replacement reaction will occur unless both of your products are aqueous. Because remember what it means for something to be aqueous. It means that you don't really have NaCl in that solution. You have sodium ions and you have chloride ions. If all you have is a whole bunch of ions floating around in that solution, both before and after the reaction, then nothing really happened. Everything's still dissolved. You need something to leave that solution in order for to say the reaction had occurred. So you either need something to be a solid, something a liquid, or something a gas. And Ms. Torlin and I decided to give you some really basic solubility rules, especially because you're not going to need to know more than this if you're going into AP. There are a lot of exceptions to this, so there are some other things that I'm not telling you that would be aqueous as well, but it's nothing that you're going to need to know for our class or for AP next year. So it's enough if you know that if your cation is an alkali metal or your anion is nitrate or acetate, that you're looking at something that's aqueous. Everything else we're going to say is a precipitate, is solid. All right. So let's look first at a couple examples of substances, and we'll just go through and we'll figure out, what state those would be in, and then we'll predict some products of double replacement reactions, and I'll let you loose to practice some on your own. So here's a set of substances, and we're going to talk about, are they solid, liquid, or gas? So if it's ionic, you need to ask, is it going to be solid or is it going to be aqueous? So calcium sulfate, CaSO4. Well, my cation, calcium, is not an alkali metal, and my anion is not nitrate or acetate. So this is going to be a solid precipitate. Okay? Sodium sulfate. Sodium is an alkali metal. Sulfate's still sulfate, but we have an alkali metal for my cation. So remember that an alkali metal as your cation means that your substance is always going to be aqueous. CO2, not an ionic substance. We don't have metals and nonmetals. It is going to be one of those three that I wrote down as a gas. Copper nitrate. All right, copper, not an alkali metal, but nitrate is one of my anions that I said if we have nitrate as an anion, then it's always going to be aqueous. Anything combined with nitrate means that you're going to have that substance in a solution, so AQ. LiF, lithium, is an alkali metal, so it doesn't really matter what it's paired up with. It's going to be part of a solution. NH4Cl, ammonium is my cation, not an alkali metal. Chloride is my anion, not nitrate or acetate. So this doesn't fall into any of those categories, so it's going to be a solid. Sodium acetate. All right, sodium is an alkali metal, and acetate's one of the other things. So whether you're looking at the cation or the anion side, this is AQ, aqueous. And silver acetate, I've got that acetate anion, so this is going to be aqueous. So let me zoom out again. If you need to go back and look at any of these, you can pause and look at that. Otherwise, I'm going to go down here and predict the products of some of these reactions and thus tell whether they're going to happen or not. All right, so let's zoom in on number 1. I'm going to combine my inner. So I'm going to end up with Ag, which has a charge of +1, and chloride, which has a charge of -1. Zinc has a charge of +2, and remember, that's not changing from side to side. Nitrate has a charge of -1. So my formula for zinc nitrate should be ZnNO3 2. Now, the annoying thing about double replacement reactions is that you need to predict what the products are in order to predict whether the reaction is going to happen or not. Single replacements were easy because if the reaction wasn't going to happen, you didn't even have to waste your time thinking about what the products were going to be. But these are not the case. So I need to then look at each of these and ask what state it's going to be. They're both ionic, so I need to look at what my cations and my anions are. Silver, not an alkali metal. Chloride, not nitrate or acetate. So silver chloride is going to be a solid. Zinc nitrate, I have nitrate there, which means that it's automatically going to be a solution. Just as a reminder, what are my rules for if the reaction happens or not? At least one of the products has to be solid, liquid, or gas. So since I have this silver chloride here, which is a solid precipitate, this reaction will happen, okay? If both of your products had this little AQ behind it, then it would be no reaction. But I have one solid, so it happens. So I need to balance this. So in order to balance it, I'm gonna need 2 of these and 2 of those. So here are the products of this first reaction. Let's look at number 2 here. So I'm going to combine the inner, combine the outer. All right, this is interesting. So my inner one, I have hydrogen and hydroxide. What do you think is going to be made when I combine hydrogen and hydroxide? Well, if I wrote it out, it would be HOH. But we know from when we were balancing that HOH is just water. So H2O, okay? I know right off the bat that's a liquid. I'm gonna write that L there. And that also tells me right off the bat that this reaction is gonna happen. It doesn't really matter what my other product's gonna be. I have a liquid there. Okay, my other product, I'm gonna have calcium, which has a charge of +2, paired up with chloride, which has a charge of -1. So my other product is gonna be CaCl2. And no alkali metal, no nitrate, no acetate. So I'm going to say that that is a solid precipitate. It's okay if one of them's water and the other one's a solid precipitate. It happens. Remember, the only thing that can't happen is both of them being aqueous solutions. I do need to balance this. So I'm going to need to put a 2 in front of here and a 2 in front of here. All right, let's look at this next one. Combine the inner. Potassium with a charge of +1, chloride with a charge of -1. So KCl. Combine the outer. I have sodium, which has a charge of +1, bromine, which has a charge of -1, NaBr. All right, states here. I've got potassium is an alkali metal, so that's aqueous. Sodium is an alkali metal also, so this one is also aqueous. So you just did all of that work only to cross it out and say that there is no reaction that occurs there. Okay, if I put sodium chloride and potassium bromide together, that's fantastic, but I still just have a whole bunch of ions floating around in solution. Nothing has changed that will make my products be any different than the reactants were. 2 more examples here. Combine the inner. Potassium has a charge of +1, chloride has a charge of -1. So I'm going to end up again with KCl. And I can go ahead and just write AQ right now because just had that above, and I knew that that was aqueous. And I'm going to end up with silver, which has a charge of +1, combined with nitrate, which has a charge of -1. So AgNO3. Now, silver, not an alkali metal, but nitrate is one of the anions that I said if you have nitrate, it's always going to be aqueous. So again, I have two products that are both still soluble, aqueous, in solution, however you would like to say that. So no reaction occurred there. All right, last one. So I included this one here because you will definitely see things like this sometimes. I have lithium, sulfate, and water. Here's the thing. Just like when we were predicting products as single replacement reactions, we need to think about water as if it's an ionic compound here. We need to have a cation and an anion to combine with things. So I'm going to break this apart into hydrogen hydroxide, just like we've done in other situations this year. Hydrogen has a charge of +1, hydroxide has a charge of -1. While I'm at it, if I split my first compound, lithium has a charge of +1, sulfate has a charge of -2. So combine my inner, combine my outer. Hydrogen is going to end up paired with sulfate. Sulfate has a charge of -2, hydrogen has a charge of +1. So my formula for that is going to be H2SO4. And then lithium is going to end up with hydroxide. Lithium's +1, hydroxide's -1. So LiOH. Before I look at whether this happened or not, which actually, no, sorry, we'll look at that first. So hydrogen falls into the category of an alkali metal, which means that will be aqueous. Lithium is an alkali metal as well, so it doesn't matter what it's paired up with. That's aqueous as well. So unfortunately, again, you did all that work to say no reaction occurred. I did not realize that I gave you 3 in a row there with no reaction. Did not do that on purpose, but meh, it happens. If you look back at these reactants, it's really, really important, guys, that you think of water as hydrogen hydroxide. Otherwise, you will not predict the correct products coming out of this, okay? When you're going to split it up into ions, it's hydrogen as a cation, hydroxide as an anion. Please don't think about it as hydrogen and oxide. You won't, it's not the way it happens. You won't get the correct products out at the end of this, okay? So again, as a refresher, charges stay the same from one side to another. Subscripts will not necessarily. You need to think about the charges to figure out the formulas. Subscripts that are part of the polyatomic ion do stay there. And then in order for a reaction to occur, at least one of your products has to be a solid, a liquid, or a gas. So you saw one example, the first one here, where you had a solid precipitate. Example 2, you had a liquid form. You also had a solid precipitate. But then the other 3, both of your products were aqueous solutions, so no reaction occurred because they're just a bunch of ions floating around in the solution. Nothing really happened. No sign of a chemical change would have happened there. To predict whether an ionic compound is aqueous or solid, the rules are if your cation is an alkali metal and or your anion is nitrate or acetate, then you have an aqueous solution. If it's any other combination, then you have a solid precipitate. Those are the rules that we're going to go with. Again, there's some exceptions to that if you look things up online, but those are the rules that we're going to go with. If you need to stop that, pause it, go back, watch it again, that's fine. Otherwise, come back into the meeting room and ask me any questions that you have, any clarification. If you want to go over a couple examples together, that's fine. If you feel like you're totally fine with this, then go on to Schoology and you can download the double replacement reactions worksheet. And that's going to be your job for the rest of class and for homework tonight. There's also a short quiz. It's not really a quiz. It's more of a survey just of what's working for you with the remote learning, what's not, what we can change to make things better, stuff like that. So thanks. Sorry class was like this today, but I figured it was a little bit less destructive than the alternative. And I will keep the Zoom meeting on the whole time. So again, please just pop back in if you have any questions about anything. Otherwise, I will see you on Thursday, and we're going to go over some combustion reactions and then a mixture of single, double combustion, all kind of mixed together with that. Have a good day.